Now we're going to talk about specific algorithms. And as I said, there are three types of method. First one is gradient, and second is Newton method, and the third one is trust ridge method. And the gradient method is based on the first order approximation, and Newton method is based on the second order approximation. And there are pros and cons in this method and this method. So trust ridge method is actually a compromise between these two approaches. So trust ridge method takes the advantage from this one and this one. So it's kind of in the middle of these two methods. Or we can use some other additional information, like a shape of objective function, okay, like Hessian or momentum, or we can consider the parameter manifold structure as in natural gradient or relative optimization, or we can think of uncertainty of gradient information in min batch as in some specific algorithm. But we're not going to talk about all the algorithms, all the issues here, but we'll talk about the natural gradient, which is quite popular in the machine learning or deep learning. So at least I hope you understand the concept and idea of natural gradient. Okay, so first one is gradient descent methods, and the gradient descent methods are quite simple. Okay, so learning is to update the parameter by this. Okay, this one is a current parameter, and this one is updated parameter, and this one is updating rule. And we have a learning rate, and we have a gradient. So gradient defines the direction of the parameter update, and the learning rate determines how far the weight should move. Okay. And sometimes in many algorithms, epsilon can change along the time, like epsilon sub t. Okay. So the idea is simple. Given this function, take a derivative. So let's say we are here, then take a derivative, and when we take a derivative, this one is a 0 and this one is negative, this one is positive. So when the gradient is negative, then we move toward right side. So we the next parameter value is on the right side of this current parameter. Or when we take a derivative, it's positive, then we have to move to the left side. So this one is on the left side of this parameter. And we start from random point. We can start anywhere, here or here. So there's no other way to initialize except random initialization. Okay. But when we initialize the parameter, then there are some approaches. Okay. So random, but is it a uniform random or is kind of Gaussian random? So depending on these policies, then the learning process will be more easier than other policies. Depending on the situation, depending on the data, and depending on the network architecture models, so we have to choose some better initialization policy. But anyway, so we can start from just random point, and then we can update. Then based on this gradient method, then every time we move and we move and we move, and then finally gradually we converge to the local minimum. Okay. And when we use gradient descent, then the effectiveness of this gradient descent method depends on the shape of the function or the learning rate. Okay. So when the function, the gradient is not normalized, then every time this one is a contour of the gradient. So if we are here, then the gradient is actually orthogonal to this contour. So we will move to this direction. And if we're here, then the next direction is this, and this, and this. And eventually we can converge to the point. But if it is normalized, then it's better. It's smoothly, it can converge to the local minima. Okay, so we'll talk about this kind of case later. When we handle this normalized case, then something like a momentum would help. But anyway, the shape, if the shape is not unnormalized, then the learning would be hard. And the next one is the effect of the learning rate. And the learning rate is large, then at the beginning of this training, then it's great. It can learn really fast. But when it is around the local minimum, then it cannot converge to local minimum because the step size is large. Then when we are here, then when we take a gradient, then we should move to the left side. Then the learning size is large, then we take a large step here. Then when we take a gradient, then we should move to the right side, and learning rate is large, then we move back and forth, and we cannot converge to this point. So that's the problem of a large rate. But when it is small, then at the beginning of this process, it takes a lot of time. Okay, so it takes a lot of steps. And moreover, the problem is here. If it is, we call it plateau. When the plateau is long, like this, then if the learning rate is small, then it will stop around here. The gradient is almost zero. But think about this, a large learning rate, then from here, okay, then we have to move to the left side, then we take a large step. Then from here, then we have a learning rate, and then we can go through this plateau with a large learning rate, even though the large learning rate is not enough to escape this plateau, but is better than the small learning rate. But if it is a small, then around this local minimum, it can converge, right? So at the beginning of the learning process, we prefer a large learning rate, and when it converges, we prefer a small learning rate. But the problem is we don't know when it is converging, right? So when the gradient is small, then is it the plateau or is it converging to the local minimum? We have no idea. So there are many different strategies to control this learning rate. Okay, then again, before talking about the specific learning algorithms, and we have to talk about this batch and stochastic and mini batch gradient. Okay, and it is about the sampling method and how many samples are we gonna use for one update. So, long time ago, before we started talking about the big data, and in machine learning we had like usually 1,000 samples or a couple of tens of thousands samples. That was it. In that case, we could use a batch gradient descent. Okay, so we can use all of them at the same time. That is the batch gradient. Okay, so in that case, we calculate gradient with all the samples and then take an average. And then with the learn rate, we update. So we use all the samples at the same time. That is good. So batch methods have a smoother trajectory than the others. But if it is a stochastic means we actually use one sample at a time. Then the update rule looks like this, with one specific sample. Okay, then in this case, learn rate should be small, obviously. But with a small learn rate, the learning trajectory looks like this, because sometimes one sample would be outlier. Okay, sometimes there is a mislabeled data sample. So in that case, this contour is based on the batch gradient. Okay, batch gradient contour. But when we take a gradient with one sample, then this one, the gradient is actually going the other directions. Okay, sometimes this direction, sometimes this. Look at this one. Sometimes even this direction is possible when the sample is completely outlier. But eventually, gradually, it will converge to this local minimum. Okay, so that is a stochastic gradient descent. But recently, many people prefer mini batch gradient descent method, which is in the middle of which is between this batch and stochastic gradient descent methods, which means we use some samples, not all of them, not just a single sample. We use some samples like 32 samples or 64. The reason why we use the 32 or 64 or 128 is that we are from computer science, so we prefer 2 to power something. That's why we use these numbers. There is no specific reason. If you want, you can use 50 or 100. It's totally fine. Okay, so usually we use the 32, 64, 128 samples for mini batch. So we take let's say if we take 64 samples, then we take an average of the gradient, then we update. Okay. Okay, now we are ready to talk about specific learning algorithms. So first one is a stochastic gradient descent. The name is simple. It's a stochastic gradient descent, but in this case we use mini batch. Okay, and the name is really simple, stochastic gradient descent, which means we don't have any other sophisticated tricks here. So we just take a gradient and with the mini batch and then update. That's it. So given a training set with x and the y target, and we define the learning rate, or we can come up with some strategy to change the learning rate. Okay, then we are going to repeat until stopping criterion meets. I'll get back to this point later. And sample a mini batch of m samples from x and y. So in the mini batch, we have m samples. Okay, and then take a gradient and take an average. That is our gradient. Okay, and then simple. Just use a learning rate and the gradient and update w. That's it. Okay, then when do we have to stop? When do we know this has converged? So actually we don't know. So there is no way to determine if it converged or not in theory, but we can come up with two different ideas. It's two similar ideas. First one is that we can stop when objective function doesn't decrease. Okay, so when we update, then we can actually check the objective function value, and the objective function value doesn't decrease with this update. Then we can say, oh, the function is kind of converged. Okay, but we are not sure. This function is stuck at the plateau. Who knows? Nobody knows actually. And second one is quite similar to that, and we actually check this gradient. So this one is the amount of update. Then when the epsilon times gradient is the norm of this one, converges to 0. So which means we cannot update the parameter that much. then we can say, oh, when we update this one, then it's not changing. The parameter is not changing with this update rule. Then it looks like it is converging somewhere. But again, there's no guarantee that, right? So as I said, it could be around here. Then we have to wait. We have to wait. So you shouldn't stop, okay? Even when the function is converging, but still wait until you are sure. Okay. Okay. The next topic is epsilon. Okay, as I said, we can fix a learn rate epsilon in advance, or we can come up with a rule to change this epsilon. But we can have another algorithms, backtracking, something like a backtracking. So we can use a line search method like backtracking to determine the best epsilon. Or simply, we can come up with this rule to change the learn rate.